Section 6. Effects. What are effects and how do they help me modify the signal I just recorded? We now know that an audio signal has three characteristics: intensity or volume, frequency, and phase. Each characteristic can be modified by cleverly placing electronic components in the sound signal path. In Table 6, basic processor or effect units, or effects, or for even lazier people, FX, are displayed. Table 6 has 5 columns: effect, type, description, result, and derived effects. Let us study this table for a bit. First, you will notice that there are three main types of effects: those who work with intensity or volume, also called dynamics processors, those who work in the frequency domain, and those who work in the time domain. Technically speaking, the phaser obviously works with phase, but since it works with phase with respect to time, it is always put in the time domain processor category. Tremolo is an effect which modulates the volume of the original signal. It is, in that sense, an offshoot of both the compressor, modulating down, and the expander, modulating up. It might look like a theoretical separation, but knowing what you are working on can help you troubleshoot what the effect is doing when the results do not sound good. Furthermore, generally speaking, cleanup effects should always be used before coloring effects for a very simple reason. You do not want to be coloring or enhancing parts of the sound that you do not like. Second, what you obtain when passing a signal through one of these effects, the results column, can be sorted out in two categories: a cleaner sound or a colored sound. A cleaner sound means that the effect has been used to remove some undesirable feature of the sound. For example, a gate might be used to clean up background noise. A compressor might be used to even out a performance. An expander might be used to bring up an interviewee's speech level to the interviewers for a better listening experience. An EQ might be used to remove some low frequency buildup from bass amp or an offending frequency caused by a cheap microphone. In all the examples above, the result is a sound cleaned up and prepared either for further processing, most likely, or for direct listening. What does coloring sound mean? The phrase colored sound might sound weird. How can a sound be colored? What most people mean by that is how their perception of the sound has been altered, usually in a pleasing way. For example, you have seen some preamps labeled as delivering a colored sound in Table 5. The preamp adds frequency content, the color, by applying the signal through a certain electronic component. In the case of effects, the same principle applies. The compressor might color a snare drum sound by letting the initial hit sound go through, but reducing the volume afterwards to tighten up the sound. A transient shaper might make a cymbal hit sound for longer by increasing the duration of the sound. A tremolo might give a guitar sound its old groovy 60s sound by rapidly varying its volume, not its frequency. No need to explain how the distortion changes the sound. You rarely hear a non-distorted electric guitar these days. An EQ might color the sound by adding high frequencies to an otherwise dull flute solo. A vocoder might restrict the frequency range of a vocal performance, giving it the famous robotic feel. A wah-wah pedal might make a guitar solo much funkier by modulating the original notes with a sweep of some frequency range. Think Jimi Hendrix. A flanger or a chorus might make a guitar sound much weirder by changing its phase and remixing the processed signal with the original. Think The Police. A delay or reverb might make a sound seem bigger by playing copies of the original signal right after the original, emulating reflections from surrounding walls. Think Pink Floyd, or any progressive rock band for that matter. Of course, these effects can be chained one after the other, making creativity with even a simple original sound infinite. The original signal can be modified with those effects by two different means, or more precisely, in two different domains. Because we are still in the analog domain, our signal still has not been converted to digital bits. Those effects would logically be produced by hardware units, which include tubes, filters, transformers, etc. Some of these units have become famous and will be mentioned in Chapter 2, Section 7. In the digital age, some of these units' effects have been modeled in software called plugins. Some of these plugins will be mentioned in Chapter 3, Section 3. These effects usually share one characteristic. The original, dry sound can be mixed with the processed, wet sound to change the amount of effect added to or subtracted from the signal. If the device does not possess this feature, splitting the signal to two tracks at mixing stage and varying the relative volume of both tracks yielding the same result. Also, each of these effects can be used to trigger other effects, yet increasing the complexity of what can be achieved with just a handful of processors. Let us now dive into what each effect does and what its main parameters are. Intensity effects. Gate. What is a gate? A gate allows a signal to pass only if it is below a certain threshold. This can be used in various situations, to clean up unwanted noise from a recording or to filter a signal to then pass on the on-off information to another signal for further processing. This is called triggering. When the signal's intensity crosses the threshold, the gate starts to open and a processed signal appears. It finishes opening when the attack time has passed. At the end of the attack time, the unprocessed and processed signals are the same. When the incoming signal's intensity gets smaller than the threshold, the gate is programmed to wait a set amount of time, the hold time, before it starts shutting down. During the hold time, the unprocessed and processed signals are still the same. When the hold time is over, the gate starts to shut down and the processed signal's intensity decreases. The gate finishes to shut down when the release time has passed. When the gate is closed, the processed signal disappears. You could also set the gate to reduce the signal's intensity by some fixed amount, the range. In the example above, the gate's range is infinite. This means that when the gate is closed, the processed signal's intensity is 0. How do you reduce a signal's intensity? That is where digital signal processing comes in. It is an engineering discipline that studies how signals are measured and transformed. In a nutshell, reducing a signal's intensity is achieved in the physical world simply by placing electronic components, filters, in its path. Circuit design determines the type of filtering. In the plugins effect world, programming models the behavior of those components. When do I use a gate? The first example of gate use would be when you are trying to take out room noise from a live recording. Set the threshold right above the noise maximum level and only the louder parts of the signal will go through. You could of course manually lower the volume of the signal every time nothing useful is being recorded, but that would be tedious and open to a lot of mistakes. Recording these knob movements, here the intensity of the signal, to replay them is called automation. The second example of gate use would be if you would like to trigger an echo whenever the vocals go above a certain loudness. You would set up the threshold high so that only the loudest parts of the vocals would be let through by the gate, and then use that information to trigger the echo. This process is called sidechaining, using the information from one signal to trigger changes on another signal. Compressors. What is a compressor? Air is a natural compressor, so our ears are used to listening to a compressed sound. That is why the compressor is one of the most used effects in the industry, trying to recreate the sensation of listening to live sound. A compressor effectively smooths out signal peaks to a more uniform signal. You can use this effect, for example, to catch unwanted peaks in a vocal or a guitar recording. You could also use it to bring more coherence to an overall recording by limiting the difference between the quietest and loudest parts. Another way of saying the same thing is a compressor limits the dynamic range of a signal. What does dynamic range mean? It is the ratio of the loudest possible intensity, or volume, to the noise floor, defined as the quietest possible intensity of the signal. By now, when you hear ratio, you think dB. We saw that a typical dynamic microphone outputs voltages in the 10 millivolt region, and that a typical processing device works with voltages in the 1 volt range. From equation 3, we know that the ratio of amplitudes x is expressed in dB with 20 log 10x, so that in our case, the ratio is 40 dB. That is the gain needed from the microphone preamp, but also the dynamic range available to the engineer recording the sound. How does a compressor work? The standard compressor has 3 main components: a level detector, a gain reduction module, and an output amplifier. The level detector's jobs are 1. To see when the incoming signal's intensity is above a set threshold, 2. How fast it has to start sending the reduction information to the gain reduction module, attack time, and 3. How fast it has to stop sending it, release time. Yes, you read that right. The attack and release times are actually speeds. Depending on manufacturers or developers, the compressor filters are even specified differently for attack and release. For example, Attack filters are usually specified in the amount of time it takes for a set percentage of the gain reduction target to be achieved, which means settling for less. That percentage ranges from 70 to 95%. Release filters are usually specified in the amount of time it takes for a 10 dB gain reduction to happen. The gain reduction module's job is to aim at reducing the signal's intensity by using a series of filters. The compression goal is called a compression ratio. You notice that I do not say compresses, but aims at reducing. It is not to be pedantic. Compressors do not simply reduce intensity. They reduce intensity by comparing the current intensity with the previous intensity, because that is how filters work. This means that you cannot just tell the signal to stick below a certain threshold. The output amplifier's job is to increase the signal's intensity by an amount called the makeup gain, so that the sound has the same intensity it had before entering the compressor. The gain can be reduced right when the information is received by the level detector, hard knee. Alternatively, it can be smoothed out by using a smaller ratio before using the full desired ratio on the signal, soft knee. You might hear some people say that a compressor brings quiet parts of the signal up. That is not true of a compressor as a part of its standard operation. It merely aims at shaving off peaks going above the threshold. Only if you make up for the lost gain by increasing the process signal's output will the quiet parts of the process signal be heard more. That is what the makeup gain is for. In the list of effects shown in Table 6, the compressor is the first major effect that you will be hearing a lot about in audio circles and online forums. One of the reasons is because it is very widely used, but I believe that it is also talked about with a shroud of mystery because it is very rarely completely understood. Let us hope that what you just read put you on the right track. Limiter. A limiter is a compressor with a very large ratio. This is of course theoretical in the analog domain, as the components used limit what the limiter can achieve. Transient shaper. What is a transient? Transient is an adjective meaning passing especially quickly into and out of existence, from the Merriam-Webster dictionary. In the audio world, a transient, as a noun, is that concept applied to a signal or sound. A lot of people talk about transients and mean the percussive element or the initial attack of the sound, like a snare drum hit or a strung guitar string. Other people mean the shape of the waveform, and that is what a transient shaper refers to, shaping the waveform of a sound. How does a transient shaper work? A transient shaper only has two parameters, which make it simple to use but very powerful at the same time. The first parameter allows increasing or decreasing the gain on the attack of the transient. The corresponding knob is usually labeled attack. You might think that this is exactly what a compressor with makeup gain does. You would be right, except that there is a difference. The compressor only works above a certain threshold, while a transient shaper diligently increases or decreases the gain on every voltage it sees. The second parameter, linked to the first, allows increasing or decreasing the gain on the tail end of a waveform. This button is usually labeled sustain or release. There usually also is a gain button to control the output of the effect. Learning how to properly use a transient shaper can be great help when a compressor does not work or an EQ is too blunt of a tool. I would even recommend using a transient shaper before starting to use a compressor, simply because it is much more intuitive and easy to understand. I know their uses are different, but there are times when increasing the gain on a transient is better than trying to make the transient coming out by reducing the range of the signal. If the compressor is the well-known superhero, think Iron Man, the transient shaper is the unsung superhero who comes out of nowhere to save your day when you think all has been lost. Think Gollum. Expander. An expander, sometimes also called an upward compressor, is the exact opposite of a compressor or downward compressor. It increases the dynamic range of a signal. In this regard, it is a type of gate. It can make quiet signals even quieter by comparison to larger parts by increasing the dynamic range of a signal. Expanders are not the most talked about effects, but are worth knowing about. Frequency effects. Distortion. What is distortion? Distortion is an effect which is caused by inserting electronic devices in the signal path to limit or clip the original voltage signal. In audio terms, the result is that frequencies that were not present in the original signal appear in the processed signal. Odd or even harmonics appear in harmonic distortion, while combinations of the original frequencies appear in intermodulation distortion. The first type will always sound musical, since multiples of the original frequencies are, for each frequency, simply octaves above the original. For intermodulation distortion, this might not be the case, since a sum or difference in two frequencies might not yield a frequency related to the original. Depending on the type of overtone added by the electronic circuit, the resulting signal will have a different shape. For example, adding an odd harmonic to the original signal will approximate a square wave, while adding an even harmonic will approximate a sawtooth wave. Combining these will affect and change the original signal in different ways. Is distortion, fuzz, and overdrive the same? The guitarists among you will want to know the difference between distortion, overdrive, and fuzz. Are they the same? Nope, they're not. Overdrive is exactly what the name indicates, pushing or driving the amplifier into generating harmonics by pushing the electronics in the amp past their intended power range. This means that in overdrive, the main goal is to gain power, with adding color a secondary objective. Thus, the processed sound is different from the original, but not by much. Distortion is the opposite. The goal is to mess the original signal as much as possible with some power gain along the way. Fuzz is obtained by inserting special transistors in the signal path which add frequencies to the sound recognizable by its warm and fuzzy character. Think Jimi Hendrix. In our effect terminology, distortion, meant in a generic sense, is clearly a coloring tool. All sorts of different devices and tricks can be used to distort the original signal. Permanently damaging amplifiers, using devices in unintended ways, etc. In the digital domain, people spend fortunes on software to try and reproduce those analog, warm-sounding distortion effects. Equalizer. What is an equalizer? An equalizer effect, or EQ, modifies the gain on certain frequencies, either down, cut, or up, boost. It is a very well-known feature of many hi-fi home stereo systems. It might be popular because turning knobs has a direct impact on the outgoing sound, any repeatable impact at that. The same applies to audio. The equalizer is the most famous effect in the audio engineer's bag of tricks. EQ effects can be simply specified with three parameters describing how the signal responds to the components placed in its path: the shape of the EQ change, the frequency at which the equalization happens, and the speed with which the effect comes into play. What are pass, shelf, and band filters? EQ shapes come in three kinds: pass, shelf, and band. A pass filter lets every frequency above, high, or below, low, through. Another opposite way of thinking about it is to talk about cut instead of pass. Low cut is high pass and high cut is low pass. I will stick to pass because I think it's more intuitive. The high pass frequency is defined as the frequency which falls below the original frequency by 3 dB. The speed, or the slope, with which the EQ change happens is usually expressed in dB per octave. Specifying this type of EQ would then mean saying that it is a 300 Hz high-pass filter at -12 dB per octave. Remember that an octave is the frequency distance between two equivalent notes, for example C3 and C4, so yes, this means that -12 dB per octave is not the same intensity reduction at 100 Hz than at 10 kHz. A shelf filter is the combination of a pass and an inverted pass filter around a specific frequency. A shelf filter can consist in high-pass filters with a cut in low frequencies and a boost in high frequencies, or in low-pass filters with a boost in low frequencies and a cut in high frequencies. Exactly like for the pass filter, the slope in dB per octave determines how quickly the changes happen. What is a first-order filter? Both filters are obtained with what are called first-order filters. In the analog world, that is what the combination of a single resistor and a single capacitor can produce. Because of their simple design, these filters can only produce those filter shapes depicted above. For more complex filters like the band pass filters, which lets frequencies within a range pass, you could describe it like a combination of a high and low pass filter, we need to go to so-called second-order filters because of the mathematical functions involved in describing the frequency response to the filter. Here, an extra parameter applies, Q. It tells us how wide the frequency range is. Q is nu0 divided by open parentheses nu-r minus nu-l close parentheses, where nu0 is the center frequency, nu-r is the right frequency when the EQ curve is minus 3 dB from its highest point, and nu-l is the left frequency when the EQ curve is plus 3 dB from its highest point. A high Q means that the EQ change will happen over a very narrow bandwidth. How do I use an equalizer? Taking frequencies out of the signal is usually associated with cleaning up the sound, for example, taking low-frequency rumble off of a bass guitar recording. Of course, cleaning up in this fashion also colors the sound in some way. After all, we are changing how the sound sounds. However, I will stick to thinking about EQ cuts as cleaning because that is the easiest way to think about it. Cuts are generally made with a small EQ, narrow width. This sounds more musical to a lot of professionals, but as always with audio, feel free to experiment. Adding frequencies is usually done with a larger Q, a wider width. Again, experimenting is the key, but starting off with a larger Q will help you keep your track sounding musical. EQ cuts should be made before applying any other effects, especially compression, while EQ boosts should be made later. The reason is that compression will bring out the quieter, more subdued part of the sound, like breaths or string noises. If you do not remove these parasites, for example with EQ cuts, they will appear to be louder in the compressed sound. EQ boosts, on the other hand, will stand out more if applied after compression, even if in theory, you could apply them before compression as well. In that case, keep the boost small and wide, otherwise compression will make the change even more dramatic. I will mention one trick you can use to find out offending frequencies. First, listen to the sound and try to determine where the issue is frequency-wise. Once you have the frequency range in mind, apply EQ to the track with a very, very narrow Q and a very, very large gain boost and sweep the frequency range going back and forth a few times. Once you have spotted the offending frequency, simply reverse the gain from a large boost to a large cut. Vocoder. A vocoder is an EQ filter applied to a vocal track. It is a good example of a coloring effect using EQ cuts. Different settings can be used, but good starting points are a lower bound of 500 Hz and an upper bound of 3400 Hz. Wah-wah. The wah-wah effect is an EQ filter which periodically in time adds and subtracts high frequencies to and from a sound. The effect name does in fact represent the effect itself. The A vowel represents the sound with added frequency, while the W represents the sound with subtracted frequencies. Time effects. Phaser. What is a phaser? A phaser, or phasor, is an effect that creates cuts and boosts in the sound frequencies by altering the sound's phase over time. The way this is achieved is by placing an all-pass filter in a single path. All frequencies go through, but the phase relationship between them is changed by varying the phase with respect to frequency. All filters alter the signal's phase because their impedance delays it. How does a phaser work? This is how it works. The incoming signal is split in two. The first signal has its phase altered as described above. It is then mixed back in the second, original signal. What happens then is that the out-of-phase signal frequencies cancel out, while the in-phase signal frequencies are boosted. The peaks thus created are unevenly spaced. This means that they are not in a harmonic or multiple relationship with the original frequencies. This gives the characteristic "eow" effect, known mostly as a guitar effect, but are also worthwhile as a keyboard effect. Phasers might have different parameters depending on how they're built, but they have at least a frequency to determine how quickly the phase is changed, a range of swept frequencies, and a feedback control to determine how much, if any, of the signal processed should be fed back into the original unprocessed signal. Feeding the signal back into the input is a way to increase the magnitude of the effect. Van Halen is known for its uses of phasers, especially in atomic punk, Jump to the 50th second. But other bands such as Queen, Genesis on keyboards, and Radiohead also used it. Delay. What is a delay? A delay mixes a delayed version of the signal with itself. The result is a single echo or a series of echoes, depending on how many times the sound is split and fed back or delayed into itself. How does a delay work? A delay effect essentially has one parameter, the amount of time the signal should be delayed by. This amount of time can be expressed in milliseconds or in relationship to the song rhythm, for example in 1/8 note increments. The latter can help keep the delay musical, meant as in with some level of coherence with the song. A feedback control might also be present like for the phaser. Because of the apparent space gained by delaying a signal by small amounts, delay effects are sometimes used to create fake stereo images from a mono signal. The danger of that technique is that when the song is listened in mono, the combing effect resulting from the addition of two delayed signals will produce the flanging effect, see below. A delay effect can be hard to spot because very short delays, 15 to 60 milliseconds depending on relative delay level, fall below our conscious listening threshold. The larger the delay is, the quieter the delayed copy can be before the effect is detected. When the delay is increased beyond our hearing threshold, it first gives a sense of spaciousness, even if our brain does not recognize both signals as being distinct. If it is increased further, the delayed signal is perceived as a distinct echo of the original sound. Delay effects are used by a lot of guitarists to thicken their sound, but perhaps the most well-known user of delay is The Edge from U2. Check out the intro to Where the Street Have No Name or One Tree Hill. Reverb. What is reverb? A reverb effect is a more complex version of a delay. It mimics the reverberation, hence the name, or reflections of a sound in a confined space. Each time the original sound bounces off a reflecting surface, it creates an echo, a delayed copy of itself for a certain listening position inside the space, which decays over time depending on the sound's frequency and conditions inside the space. Reverb is what you hear when you place a source in a room, play it, and then abruptly stop it. Those multiple, slightly altered, less powerful versions of the source sound are interpreted by our brains as an indication that the source was played in space. What is RT60? The time it takes for the sound to die off is called RT60 for reverberation time. It is the time it takes for the signal to decay by 60 dB. RT60 depends on the volume of the space V and on the inverse of both the total surface area of the room S and the absorption coefficient A of the material used to define the space, valued at 20 degrees Celsius or 60 degrees Fahrenheit. RT60 is approximately 0.16 times V over open parentheses S times A close parentheses. It also depends on the frequency of the sound through the absorption coefficient. In a typical room of 3 meters by 4 meters by 2.4 meters, roughly 10 feet by 13 feet by 8 feet for you imperials out there, RT60 is about 0.08 over A. For plaster walls, A is approximately 0.02, so RT60 is 4 seconds. Make your walls hardwood, A is around 0.3, and the time falls to 0.267 seconds. I'm not going to make this an acoustics discussion, but the way your recording and mixing space is built and treated if necessary is much more important than the gear you will buy. This is discussed in details on the interwebs. What are the different types of reverbs? The first analog reverb effect is to simply play a pre-recorded sound in a room and have a microphone pick up the resulting sound. This is called a chamber reverb. The second type of analog reverb is the plate reverb. Sound is sent through a speaker-like device to the center of a thin metal sheet suspended in a soundproofed box. Pickups are mounted on the plate to detect vibrations induced by the transmitted sound. Those vibrations move from the center of the plate to the edges of the plate and then back, like ripples on a pond. Because sound travels in a circular fashion and since the plate is usually rectangular, the reflections coming back from the edges add complexity to the vibration transmission patterns, creating a complex network of reflections which give the reverb a lush, dense character. The decay time of the plate can be altered by adding damping material on its surface. Because of the way plate reverb works, it does not adequately mimic a reverberated sound in a physical space. Thus, plate reverbs are usually used to color a sound rather than to give it a sense of space. The last standard kind of analog reverb is called a spring reverb. It works by replacing the metal sheet with a spring, the sound reverberating up and down the spring. The resulting sound is more metallic and usually needs to be shaped by EQ to sound more musical. What parameters does a reverb use? Reverb parameters are many and of course change depending on the type of reverb, but here are a few. First, the early life of a reverb is described by how early reflections behave. This parameter describes how many and how strong they are. Some reverb processors even allow you to define first and second reflections individually. Second, how reverb behaves in time, tail reverb, is defined with pre-delay, amount of time between the initial reverb and the appearance of the tail end of the reverb, decay time, related to RT60, also sometimes called damping, and diffusion, how longer-lasting early reflections interact with the reverb tail. Other parameters allow the reverb to be shaped further. For example, mid-side or stereo width allows controlling the dispersion of the reverb in the stereo field, or EQ filters can make the reverb brighter, low-pass, or darker, high-pass. Flanger. A flanger is a type of delay where the delay changes with time. This gives the characteristic EOI effect like the phaser, but with more pronounced and deeper E sounds than for the phaser. The sound of the effect is sometimes compared to a plain swooshing effect. Flanging sounds more natural to some people because the peaks obtained by adding a delayed version of a signal onto itself are evenly spaced. They are harmonically linked to the original frequencies. Flanging is used primarily for guitars, but can be used on any other instrument. You can find a list of recordings where flanging is prominent on Wikipedia. Chorus. A chorus mixes the original signal with a copy of itself that is both delayed and frequency shifted. The frequency or pitch shifted signal is usually modulated with low frequency oscillator, LFO. This means that this increase or decrease in frequency of the original signal follows a sine type wave with a low frequency. The result is a sound which appears to have multiple voices slightly different from one another. For example, Pull Me Under by Dream Theater has a clean chorus effect on the guitar at the beginning of the song. Section 7. Outboard gear. What is outboard gear? Depending on the taste and budget of the recording engineer, the amplified electrical tension representing the signal containing our frequency information can be directed to outboard gear to pre-process the signal before entering the digital domain through the analog to digital conversion. It is called outboard gear to contrast with devices available in or on the board, mixing console, or nowadays with software available in the box, ITB, meaning on the computer. Note that outboard gear seems only to concern gear being used before the digital domain, even if technically speaking, whatever device is used after the digital domain also is outboard. Some people put mic preamps in their outboard gear list. Although this is technically correct, I prefer to follow the logical signal path and talk about preamps just after microphones. From now on, whenever I mention outboard gear, this includes mic preamps. Should I use outboard gear? Whether outboard gear should be used or not is a matter of personal preference. If you do not know exactly what you want to achieve when you are recording a sound source, leave the signal unprocessed for as long as possible. This will let you add or correct aspects of the sound later. If you do know what sound you are looking for, and if you know how what you are currently hearing through monitoring will come out after layers and layers of processing, then pre-processing can be a very effective tool to gain time and energy in the mixing process later. Most professionals use outboard gear to pre-process the signal as a part of their magic. Compressors. Hardware compressors play a large part in how professional studios treat the analog sound. You will find a few models with their classical use in the table below. Some of these hardware units have received the digital treatment and are available as plugins from various software companies. Do they sound as good as the original analog fathers? You will be the judge of that. Table 7 displays hardware compressors from API, Art Pro Audio, Empirical Labs, Fairchild, FMR Audio, Solid State Logic, Summit, Teletronics, Universal Audio, and Neurai. It has 4 columns: Maker, Model, Price, and Use, with prices ranging from $200 to $6,500. Equalizers. Equalizers might not be everyone's first choice of outboard gear. Preamps and compressors seem to be. But hardware EQs have their aficionados who will swear by them for their tone and coloring abilities. Table 8 displays hardware equalized from API, Ashley Audio, George Massenburg Labs, Kush Audio, Lang, Pultec, Rain, and Speck Electronics. It has 3 columns: Maker, Model, and Price, with prices ranging from $380 to $3,700.